There
Yeah.
we go.
We're ready to
Does
go.
that look as though it's recording?
Yeah, it is ready to go.
Okay, I think I'm going to start today by explaining something that's very simple and very important. It's something that was discovered, as far as I know, first by Weinberg back in, I'd say around 1980. The idea, right. So as I said, I was going to explain, let's see, if people are coming in late, maybe I'll start with something else that's a little less important, and then I'll go to,
Can I ask a quick
well,
question?
maybe I'll stay with what I was going to say. So the idea is integrating over fields of high mass. In fact, I think I'll restate that. Over fields of masses huge compared to the scale of the standard model or whatever scale one is working at. So this was, as I said a moment ago, this was invented by Steven Weinberg around 1980. And it's one of those things that is really simple when stated in terms of path integrals and less simple when stated in the traditional way in terms of fields expanded and creation and annihilation operators. So that's the way it is with two different formulations of the same theory. Some formulations are well suited to certain problems, other formulations are well suited to other problems. And it turns out that this is something very simple, very well suited to path integrals. So let's just, to write this in the simplest form, let's simply suppose that this is minus a half dA phi minus m squared minus a half m squared phi squared plus g psi bar psi phi d4 x. So suppose that is the action, and so this is a simple example of such a situation. So psi is some Fermi field, spin 1/2 field. Phi is a field with a huge mass represented by a capital M. Okay, and I'm ignoring any other terms in the interaction. I'm just trying to focus on what's simple. Now, if we're concerned with physics at low energies, and because if you're trying to explain something that you can actually observe experimentally, then you really are concerned with momenta that are below several TeV, or let's say below 100 TeV. And if this mass scale m instead is huge, like 10 to the 15th GeV, 10 to the 16th GeV, or it's the Planck mass, then the momenta that are associated with these derivatives where I'm thinking of neglecting those terms compared to m squared. So I'm saying that we will neglect these derivatives and then what we have is a simpler action minus a half m squared phi squared plus g psi bar psi phi d4 x. And now we can complete the square. And so what we have is minus a half m squared phi minus g over m squared psi bar psi squared. And then we have to compensate for this term. And so what we get here is g squared over 2m squared psi bar psi phi altogether d4 x. Actually, I'm a little worried about the time derivatives of these fields because the time derivative of phi, one would expect that it would be an e to the I m term, which would be of the same order as that. So I may be simplifying too much, but this is what I worked out for today. So let me just go with it for the moment. Is there a question?
No, I was just,
Let me pay the videographer. Is anybody hungry?
no, I have a quick question about videos though. Is there a video for Monday's lecture?
No.
No, no one should.
I'll explain that after class. Okay, so this is the action. So then the path integral the idea is to integrate over the heavy fields. And now one could say, and in fact the way people looked at such things before Weinberg made this particular discovery, he's made so many, is that people would just hope that the high energy scales, the high energy fields didn't matter. What we can do here is shift phi to, well, first let me write this path integral. Let's see, do I write it as, yeah, that's right. Okay, so this is e to the I integral minus a half m squared phi minus g over m squared psi bar psi squared plus g squared over 2m squared psi bar psi squared d4 x. And now if we shift the field phi to phi plus g over m squared, oh, I forgot the most important thing, d phi. So we're integrating over the heavy fields. And so the whole path integral requires us to integrate over the spin 1/2 field psi and any other fields that might be in the theory. But I'm just focusing on the heavy field and the fields with which the heavy field interacts, and in this case, that's only phi. So now if we shift, the Jacobian is just 1, and we have e to the I integral minus a half m squared phi squared plus g squared over 2m squared psi bar psi squared d4 x d phi. And now the integral over phi, the path integral over phi is is not only a Gaussian, but it's a trivial Gaussian that just gives you a factor out in front that is independent of all the fields. So the net effect is to add to the action a new term due to the heavy field, and that new term is g squared over 2m squared psi bar psi squared. So that's the idea, that if we do the path integral over the heavy fields, the result is simply to produce in the action of the standard model fields or the low energy fields a new term. And what you see here is that this new term is not renormalizable, because the dimension of a spin 1/2 field in four-dimensional field theory, four-dimensional space-time, is 3/2, so this is cubed. Squared is 6 dimensions, and we divide by m squared, so it becomes dimension m to the 4th, which is correct, but the psi bar psi is non-renormalizable, and it doesn't mean it's nonsense or that we can't calculate with it. It just means that it's not a term that occurs in the standard model. So something similar can happen in a theory with gauge bosons here. If we just keep the mass term minus 1/2 m squared, we imagine then that we have a gauge boson YA, and that's interacting with a spin 1/2 field psi through gamma A psi YA, like that. So if we imagine that this is the part of the action that we focus on, well, then we can do the same trick. We can rewrite this as an integral minus 1/2 m squared, and this would be YA minus, and now I didn't write this down explicitly, so it's G over m squared psi bar gamma A psi squared. And by squared, of course, what we mean here is YA minus G over m squared psi bar gamma A psi. And let me just do the arithmetic here. That gives you a 2, which cancels that 2. Yeah, okay, so this is correct. And then the term that we need to add in order to cancel the term that comes from here is g squared over 2m squared, and it is psi bar gamma A psi bar gamma A psi. So this again is a non-renormalizable term for the same reason that this one is non-renormalizable. However, you notice that both terms are small because m squared is huge. And so this is a non-renormalizable term arising from the fields that are many orders of magnitude heavier than the fields that we know about experimentally, or that are detectable in with current experiments. So as I said, this leads then to a new term. The new term in the interaction is S of y, which is then g squared over 2m squared
psi bar gamma A psi bar gamma lower A psi.
Now, it turns out that this type of interaction was actually invented about 80 years ago by Fermi. In the early days of weak interaction theory, it was known that a neutron would decay into a proton plus an electron plus, well, one didn't know what the, one first knew that it would be an electron antineutrino, and so Fermi wrote down a theory in which the interaction was written as G sub f times, I guess it was psi bar n, and then he put a gamma because he wasn't sure what type, whether it was a vector interaction, which would be gamma A, an ordinary gamma matrix, or something else. So he called that a gamma, and this would be psi proton and psi bar gamma. Let's see, we're creating an electron, so, and we're annihilating, all right. So it looked like that. So that was the model of the weak interactions that, so let me just call this L weak, or L Fermi. And of course, G Fermi, well, I don't remember what it is, but it's essentially 1 over the mass of the W squared, apart from something of order 1 or 1/10 or 10. And it's because on the scale of this interaction where the momenta were, let's say, MeV energies, here we're talking MeV, in the ordinary weak interactions, the big mass M was 100 GeV, or 80 GeV for the W, 90 or so for the Z, and so he proposed this form, which in fact satisfied all experiments. In fact, it was about another 30 years, or at least another 20 or 25 years before Gell-Mann and Feynman finally settled on the fact that gamma was gamma A times 1 minus gamma 5, or 1 plus gamma 5, depending on the conventions. So this was the maximum, the B minus A theory, vector minus axial vector, which is the theory that maximally violates parity. And in my view, it's an ugly feature of the standard model, but beauty's in the eye of the beholder. Many people think it's gorgeous. So, yeah.
I missed what the capital G is.
G is just a coupling constant.
And what is, it's 1 over, 1 over mass of what?
Well, mass of the proton.
The proton.
Oh, well, mass of the W, or the mass of the Z. The way it's actually written is like 10 to the minus 5 m proton squared. I think that's the way people write it. And MW is 100 GeV, so this is 100 mass of the proton. So that's a 10 to the 4th, and then divide by pi squared, you get 10 to the minus 5.
So is this still, is that Lagrangian, you called it the Fermi Lagrangian, I guess, is that still current, or is that sort of a dated way to...
Well, this was,
I
I think 1934, and this was the best that one could do then, and it was replaced then by another advance by Weinberg, but also by Glasgow and by Salam. And in fact, there's actually another person who deserves some credit here. And I once spoke with him, Ward. Ward may well have been cheated out of a lot of recognition here. The one issue is that they've got a rule with the Nobel Prize that you can only have 3 on a Nobel Prize, and they have to be all breathing. They have to all be alive. And some people say that Ward deserved as much credit as Salam, and that Salam deserved a lot less credit than Glasgow and Weinberg. But I don't know. I'm just repeating the gossip. And I'm not even sure that I'm repeating the gossip accurately, let alone, I mean, gossip may be wrong also, of course, which is why I call it gossip. Okay, let me now go to what is the correct way of doing this, namely that whereas over here I was talking about the scale of grain unification or some mass scale that's hundreds or thousands or millions or trillions of GeV higher, of TeV, in other words, 10 to the 15th GeV, 10 to the 19th GeV. Those are the huge scales that I was talking about. This scale of 100 GeV, which was inaccessible in Fermi's time, is one that has been explored at the Large Hadron Collider by the Europeans at CERN. And it was, the model was invented by, as I say, Weinberg, Glasgow, Salam, and Ward. Let me start with the linear sigma model. And so this is one of the topics that last semester we didn't know if we were going to be teaching the second semester of quantum field theory, and so I was rushing through a lot of material. I'm going to go through that material somewhat more slowly now, and this is then the idea of spontaneous symmetry breaking, Goldstone's theorem, and then the model of Weinberg, Glasgow, Salam, and Ward. So this is minus a half dA phi minus a half m squared phi squared minus lambda over 4 phi to the 4th. So this is the simplest case. Now this is just an ordinary theory of a single massive spinless boson that has certain self-interactions. But if we change it, so I'll call this L1, if we change it this way, we change the sign of m squared phi squared, then what we see is that the energy now looks like this. This is the potential V, where we're drawing the field phi like that. So it has two, well, in fact, the way I've drawn it here without any, the way I've drawn it here, it goes below the axis and is 0 at phi equals 0. So this is the phi axis, and this is V. So there were two minima, one at phi minus, one at phi plus, and the potential is minus a half m squared phi squared plus lambda over 4 phi to the 4th. And so what we imagine is that that because of these derivative terms, the energy of a field that involves both phi plus and phi minus is high, and so the true vacuum will be either something that clusters around here or something that clusters around there. And if we pick the vacuum phi plus, then that mean value will be phi plus, and this will be the minimum of this. And the minimum of that, the easiest way is to differentiate with respect to phi squared, and so that's 0 is equal to minus m squared over 2 plus lambda over 2 phi squared, and so that's at phi squared equal to m squared over lambda, so this is equal to m over square root of lambda. And we're going to call that plus or minus v. V for vacuum. And
on the plot of the potential that you've drawn, you have that phi minus and phi plus around just as those neighborhoods in the minimum. Those are the minus vacuum and the positive vacuum, right?
Right, right. In other words,
should they be zero, or what is
in other words,
phi?
This theory the way I look at it is that this theory, first of all, if we were in one time dimension, zero space dimension, just doing quantum mechanics, the true vacuum would be a linear combination of the two.
Right.
And it would be sort of complicated, but we could treat it numerically using a laptop computer and get the vacuum energy to arbitrary accuracy, no problems. In 3 space and 1 time dimension, my intuition is that this is a theory with 2 vacua of equal energy, and one of them, the field is concentrated in phi plus, the other one, the field is concentrated in phi minus. Now, if you talk about excited states, the excited states overlap, the excited states have field in both regions. All right, that's the way I think of it.
So here it's inherently, there's no uniqueness prescribed to the vacuum energy.
Give me that again.
There's no inherent sense of uniqueness.
There's no what?
The vacuum is not unique here, like it would be in quantum mechanics.
That's what I think. Now this is a subtle issue. For example, if you can take this theory and you can put it on a lattice. Now on a lattice, what happens? I think on the lattice, I think there are 2 vacua also on a lattice. But look, if you ask me what is really true, I haven't thought deeply about this in a while, and I can only say that the actual quantum field theory, I don't know. I think that there are 2 vacua, and in one field they are there, and the other one they're there. Yeah.
I remember doing this last semester, but I don't remember how you got to that lambda over 2.
What lambda over?
So the equation bottom left,
Oh, I differentiate with respect to phi squared.
what's that?
I differentiate v with
right.
respect to phi squared
As opposed to
instead of
phi.
phi
Right.
because it's easier.
Right.
I mean, if you want to check, if we differentiate with respect to phi, then what we get is minus m squared phi plus lambda phi cubed. And now we cancel one factor of phi, and we get 0 equals minus m squared plus lambda phi squared, which gives us the same result. So mathematics is saved. Okay, now the standard thing to do is to say that phi of x is a constant v, and I'm going to choose v to be m over square root of lambda plus sigma of x. Now, one of the unfortunate things about this notation is that a Greek sigma and an English v look similar, especially if you're writing them on a blackboard. But on the other hand, it is the sigma model, so that's sigma, and this is v for vacuum. So, I don't know, so if we write down what the Lagrangian is then in these new terms, it's minus a half dA sigma plus m squared over 2 v plus sigma squared minus lambda over 4 v plus sigma to the 4th. In fact, I think what I'm going to do is I'm going to write v as just a, oh God, it looks like a nu now.
Yeah.
Well, I don't know, maybe, I don't know what to do. Anyway, if we write that down, then after expanding everything, let me just tell you what you get. You get minus a half dA sigma minus m squared, sigma squared minus square root of lambda m sigma cubed minus lambda over 4 sigma to the 4th plus m to the 4th over 4 lambda. That's at least what I got. I'm just, well, all right. By the way, if you find a mistake in these notes, please send me an email or tell me. On the class web page, these things are listed under class notes. And another, I forget what the other one is called on the, it might be called masses. I also have a write-up called masses, which is on the class web page. There are several things on the class web page. If you click on the links, you'll see what they are. So what is this? This is a particle of mass m sub sigma equal to square root of 2m. The square root of 2 is because the real mass term has a 1/2 in it. And if you take the limit lambda going to 0, then you get back to this theory again, the limit of lambda going to 0. Now, this is the simplest linear signal model. The general linear signal model is a little more complicated. It's L is equal to minus a half sum on I equals 1 to n dA. Of course, A goes from 0 to 3. That's the way I'm doing these. I'm just trying to avoid too many extra Greek letters. Plus a half m squared sum phi I squared I equals 1 to n minus a quarter lambda sum phi I squared I equals 1 to n squared. Okay, so this is the ordinary, this is what people normally mean by the linear signal model. And I'm going to set phi squared equal to phi 1 squared plus dot 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 plus phi n squared. And I'm going to rewrite this L as minus a half dA phi I dA phi I plus m squared over 2 phi squared minus lambda over 4 phi squared squared. Okay, so that's the picture, and it's just basically n copies of this theory that we already analyzed, and so if we study this version, then we should get to well, we should understand this one in terms of what we've already seen. Now, this linear sigma model is invariant under orthogonal transformations. Here, O transpose O is the n by n identity matrix. This is the group ON, and this is, of course, a continuous symmetry. The minima of this are the points on the sphere phi squared equal to phi dot phi, which is m squared over lambda, where the length of phi, which I'm going to call v, is m over square root of lambda. So it's very much the same as the one-dimensional model. Well, it's similar, but now what happens is that whereas here we had a discrete symmetry, a reflection symmetry, so the group was, I guess it's called Z2. Over here, we have a continuous symmetry, ON. So it's a continuous symmetry. And what people do when typically is they write phi I this way as pi 1, pi 2, dot, 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 pi n minus 1, comma, v plus sigma. So that's the way people normally parameterize this. So the idea here is that whereas there the vacuum was one of two equivalent points, here it's quite different. We have a whole sphere and we just pick a particular point on the sphere, so we have a whole sphere of equivalent vacua, and the general feeling is that or the belief, or let's say my belief, but I think most people believe this, is that vacuum of the quantum theory is clustered about a point here, and it could be any point, but so what we have is that it's hard to describe it. I guess we can say that the theory has infinitely many asymmetrical vacua, each of which is part of a symmetric set of asymmetric vacua. I'm following Gell-Mann's term.
It kind of hurts my brain. So.
What?
That's really
It kind of hurts my brain to try to picture it.
to have it be on a.
I agree. Let's not knock ourselves out,
Some,
though.
equipotential surface being the sphere, I guess, right? Or that would be a sphere, in this case, a sphere in n dimensions.
Oh, yeah, it's an n-dimensional
Yeah.
sphere.
But it's still infinitely many equivalent vacua on the
Yeah.
on an n-dimensional equipotential spherical surface.
Anyway, so that's the picture. And so now if we take this vacuum and we substitute for phi this thing in terms of pi's, what we get after a certain amount of algebra, which I have worked out in the notes, the online notes, but which I encourage you to look at with skepticism, and if you find something wrong, tell me. What I find after all of this is the following. Minus a half dA pi I, so this is a sum over n minus 1 fields, minus a half dA sigma plus a half m squared times pi squared plus v squared plus 2v sigma plus sigma squared minus lambda over 4 pi squared plus v squared plus 2v sigma plus sigma squared, and in this expression m squared is equal to lambda v squared, and so there are considerable cancellations, and the final result then is that L is minus a half dA pi I minus a half dA sigma minus m squared sigma squared minus m square root of lambda sigma pi squared minus m square root lambda sigma cubed minus lambda over 4 sigma to the 4th minus lambda over 2 pi squared sigma squared plus lambda over 4 pi to the 4th, that's pi squared squared in other words, minus m to the 4th over 4 lambda. So that's the expression that I got, and this describes one field sigma where m sigma is square root of 2 times m, the mass parameter, and n minus 1 massless fields, massless scalar fields, pi sub I, and these are called Goldstone bosons. Goldstone bosons are the massless fields that occur when a global symmetry is broken. So if you have a theory of scalar fields with a global symmetry, a global continuous symmetry, and the symmetry is broken, you get some massless fields. And this was a theorem that Goldstone discovered and proved, and then Goldstone and Weinberg and somebody else, it might have been Glashow, wrote a paper in which they proved Goldstone's theorem 3 different ways. And yeah.
So can I assume that on that last Lagrangian over here, where you have dA pi I, that those are lower and upper, so we're summing over all the i's?
The i's are all lower because they are not Lorentz indexes. The i's are, so maybe I should have put in explicitly here, sum I equals 1 to n minus 1. These
Okay.
i's are just these guys.
Right, I just want to make sure we're summing is the main thing. Yeah.
Yes, we're, oh, no, it's my mistake. I raised this I by mistake. All right, here, let me give you.
No.
Yeah,
You-
I'm fine with the candy. I'm okay.
All right, well, you can. And I probably owe you a candy also.
I get another one.
All right, so let me prove Goldstone's theorem now. And there's actually an interesting aspect to it that I worked out. I don't know if I'll have time to describe it today. But it's something that is, I haven't seen in any textbook. That doesn't mean that it doesn't exist, of course. And I'm sure Goldstone knows all about it. And, of course, Weinberg knows everything. So let's... So this is our field. Again, we're going to have an ON continuous symmetry. And I'm just going to let the potential be d of phi. I'm not going to say what it is exactly. But the key thing is that if phi prime I is OIK phi k, then V of O phi, well, let's use the simpler notation since this is real, of O phi dot O phi is equal to V of phi dot phi. Okay. So that's what we're saying. Okay, that V is V of phi. I'll just write it as phi squared. Now, what we know here is that at the minima, so let us say at a minimum, of V, partial of V, with respect to any particular phi j, has to vanish. And I'll call that at phi squared 0, at a minimum phi 0 of V. And once again, the minima are lying on the surface of a sphere in n-dimensional, real n-dimensional space. The mixed partial derivatives have to form a positive matrix at a minimum. These are the mass squares, God, I wish I had a pen. Anybody have an extra pen?
I mean, I only have this one. You can use
Yeah,
it.
all right, never mind.
Yeah, you can use it if you need to. It's to make.
No. Thank you, though. So masses are non-negative, and these are, now, why are the second derivatives at a minimum, the second derivatives form a positive definite n by n matrix. It's positive definite because you're at a minimum, and so a second derivative can be 0, or it can be positive, but it can't be negative. We're not talking about a saddle point here. It's an actual true minimum, and so it could be 0, well, minimum in the general sense in which it could be flat, but it's certainly, there's no question of it's going down. And so near each potential, the v of phi squared is equal to v of phi 0 squared plus a half phi k minus phi k0 times phi L minus phi L0. And, of course, I left out the key parameter, m squared KL. Okay, so that's just re-saying what the potential, well, when I say it's equal to this, I'm ignoring, plus higher order terms that I'm ignoring. The point is there's no linear term, and we're ignoring any higher order terms.
Is that MKL?
And these m squareds are all positive, huh?
Is that that coefficient you just pointed to, is that MKL squared over 2?
Yeah.
Okay.
Sorry.
No, that's all right. That's what I thought it was. That's why I wanted to make sure before I wrote it down.
Yeah. Okay, so near the minimum, let's look at an infinitesimal orthogonal transformation that's near the identity. It's I theta r tr. Of course, this is physics department language. In a math department, this would be laughed at. And the mathematicians are probably right. They would just take the I, put it into the TR, and say that should be a imaginary symmetric matrix, so that anyway, this whole thing is oh God! Now I'm so used to the physics language that let me stay with the physics language. The TRs here are real and symmetric. Let me just make sure that this. In any event, they're Hermitian. And so now here's the key point. The key point is that the partial of B, let us say phi squared with respect to theta r. Well, this is partial B of phi squared with respect to phi j times the partial of phi j with respect to theta r. So let's consider changing the fields a little bit. We have parameters theta r, and in this case, if it's ON, I think there are n minus 1 over 2 parameters. Does that sound right? anyway, it's of the order, it's of that order. Real parameters that we're talking about, and these are 0 at all values of the fields. Now, in particular, phi j of theta is phi j of 0 plus I theta sub r T sub r jk phi k of 0. So these k's run from 1 to n. So we haven't split things up into pi's and sigma. Everything is a phi. And so these vanishing derivatives here are partial v, partial phi j, partial phi j, partial theta r. This is equal to partial v, partial phi j, I tr jk phi k. And this is 0 for any value, for any field, because this is due to symmetry. Now, at a minimum, we have an extra result. At a minimum, the second derivative is, well, first of all, the second derivative always is partial phi j, partial phi l. Wait a minute, I just skipped an equation here. This thing is true for arbitrary, at all values of the fields, this equation, because it's symmetry, yeah.
I can't tell exactly what that equation, partial v with respect to phi j, on the right-hand side, what's right after that? The right-hand
Partial
side.
phi j with respect to theta r.
Other side of the equal sign.
I think it's a semicolon.
Partial v, partial phi j, I,
Oh,
tr, the rth Hermitian generator of On, matrix element jk phi k summed over k.
so that, the left side, the whole thing is 0. The leftmost side from the chain rule goes to 0 too.
Say that again?
No, the partial v with respect to phi j, the leftmost side, I see that the right side is 0 from the above form, but the left side, I guess, I didn't realize that. I thought that was a semicolon.
Well, this is just equality.
Yeah,
Because partial phi j partial theta is I times that.
yeah.
Because, yeah, you left the room when I did this. What I said was, this is O of theta. Near the identity. And so did I write this down? Maybe, I think I should have written this.
No, you have it up, it's essentially the line above. Partial phi j.
Yeah, there it is.
Yeah.
Phi j of theta is phi j 0 plus I theta r. We're summing over the generators. So this is like, let's see, for n equals 3, there are, I guess, they're real and symmetric. So there are 6 generators for, no, there are only 3 generators for O3. Right. And so they're real and anti-symmetric. All right, this is screwed loose somewhere in what I've been doing, because
Are they
3 is 3 by 3. They're real and anti-symmetric in order to be 3. So you basically play with these 3 numbers, and things have to be 0 on the diagonal for the generators.
If they're real and anti-symmetric, then it's not Hermitian. Correct.
Yeah, that's
So if they're complex and anti-symmetric, you'd have.
Oh, you're right, they've got to be, it's funny, when I actually computed the things explicitly, they were real and symmetric,
That's true. You
and,
have them at the same time.
and that is, and so they were Hermitian, so I was happy, but now counting them, I'm getting only 3 for O3, and so,
I don't remember how this took out in Georgia.
So are the T?
well, actually, you know, if they're real, they have to be anti-symmetric, because they have to be Hermitian, and they can also be imaginary and symmetric. Those are the 2 possibilities for the generator's T. All right, anyway, let's not fuss with this. These are the Hermitian generators of ON, and they're apparently real and anti-symmetric. I think that's probably right. Okay, real and anti-symmetric. Anyway, this is irrelevant. The proof doesn't have anything to do with that. But, so let's leave them as real and anti-symmetric. The T's. So the T's are real and anti-symmetric. And there's a screw loose in something that I did here, because I had them real, I had certain matrices real and symmetric.
So, I'm sorry.
Yeah, if you
It'll
want.
stick in my-
No, we've got
So
plenty of time.
What needs to be Hermitian here? Is it the T sub R?
The generator, yeah, the T sub R have to be Hermitian. Because, you know, this is a physics department. The transformation has to be unitary.
Alright, so the T sub
Okay.
R,
So, U is e to the I theta R T R. The T's are Hermitian, the thetas are real. There's an I to make the thing unitary. Now, in this case of ON, the unitary matrix is also real and orthogonal. If it's real and orthogonal, then the TRs are not simply Hermitian, but they're real and anti-symmetric. But of course, now if they're...
so
I agree, there's something... I've got confused about something, because if the T's are real and anti-symmetric,
then they're not Hermitian, but I times the T
then
would
I
be Hermitian.
times them... Oh God, you're right. Right, they're imaginary and anti-Semitic. Imaginary. The T's are imaginary and anti-symmetric. IT is then real and anti-symmetric, and that makes them orthogonal. That makes the whole thing orthogonal. All right. So the T's are Hermitian. They're imaginary and anti-symmetric. IT is real, and it is then real and anti-symmetric. Okay. All right. So I hope we've got that straight. Now, this derivative, this expression here, this first derivative expression is 0 for all values of the fields. So consequently, its second derivative is always 0. And the second derivative then is we're going to differentiate this with respect to phi L, say, then what we get is I TR JL, no, JK, phi K, plus partial B, partial, well, let's leave out the phi. Partial B, partial phi J, and now we're differentiating this with respect to phi L, we get I TR JL. So this is 0, and this is again 0 for all values of the field, whether or not we're at the minimum. But when we're at the minimum, the first derivative vanishes because we're at a minimum. So consequently, at a minimum, which I'll write as phi 0, this term vanishes, the sum is 0, and so we're left with partial v at phi 0, or phi 0 squared if you want. Partial phi j, partial phi L, ITR J K phi K 0 equals 0. But this second derivative at a minimum is the mass matrix. So this is m squared JL. I'll cancel the I. TRJK phi K0 is 0. What does that say? That says that there's a certain eigenvector and I'll write this as I'll write it as phi 0 star, no, star is bad, phi 0 tilde. And phi 0 tilde is TRJK phi K0. So phi K0 is the field, the values of the n fields at a minimum. TR is a generator. This is an eigen, it doesn't vanish, okay? So if this vector doesn't vanish, then it's an eigenvector of the mass squared matrix with eigenvalue 0. So, what does that mean? That means that for every generator phi TR that does not annihilate the vacuum, there's a massless scalar boson, a Goldstone boson. So for every generator TR well, that doesn't, all right, so with non-zero, it's just TR times the vacuum vector. So you take the vacuum vector, multiply by TR. There is an eigenvector of the mass squared matrix with eigenvalue 0, so a massless Goldstone boson. But as you know, if the eigenvalues are different, the eigenvectors are orthogonal, but here the eigenvalues are the same, they're all 0. So these eigenvectors need not be orthogonal. So
there are at most as many massless scalar and we call them Goldstone after Jeffrey Goldstone, who is a professor at MIT, bosons. There are at most as many massless scalar Goldstone bosons as there are generators of the symmetry, so in this case of ON, for which TR times the vacuum vector is not 0. You see, if TR annihilates the vacuum vector, then this equation here, this part is 0, and a vector that's 0 isn't an eigenvector. An eigenvector has to be a non-zero vector. So, basically, as long as the generator doesn't annihilate the vacuum vector, the product of the generator times the vacuum vector is a potential Goldstone boson. But if you line them up, you only can take, there are only as many Goldstone bosons as there are linearly independent eigenvectors.
Can these be observed experimentally?
All right, let me think. I don't think we have any exactly Goldstone bosons. And one of the reasons for this, by the way, may be, now here I'm being very speculative. I might as well speak into the camera. The reason may be that recent results in string theory suggest that the only way you can combine gravity with consistently with other fields in a quantum theory is if any global symmetry is gauged. So it has to be a gauge symmetry. But if it's a gauge symmetry, then this Goldstone thing takes on a whole new flavor, and that's where the work of Weinberg, Salam, Glashow, and Ward come in. And I guess we'll just do that next time, since we're basically out of time here.